The voice agents we built in this episode 1 and 2 have one voice, one character, one sound. For a lot of use cases, that's fine. An AI receptionist answers the phone, it has a voice, you configure it once, and it stays consistent. That works. But what happens when your agent needs to represent multiple entities? A museum guide that what speaks for each exhibit, a language learning application where different characters have different accents, a role-play game where NPCs have distinct voices, a customer service agent that needs to switch between a formal tone for billing and a warmer tone for support. In those cases, a single configured voice is not enough. You need voice as dynamic property, something you generate contextually on demand based on who or what the agent is representing at any given moment. That is what this episode about. We are going to build the talk to the statue pipeline. Point to a camera and entity, a statue, for example, a painting, a historical figure. Use OpenAI Vision to classify who or what it is. Generate a period-appropriate synthetic voice on the fly using the ElevenLabs Voice Design API, and switch between multiple voices within a single agent session as the user moves exhibit to exhibit. This is episode 3 of the voice engineering series. Let us build it. Let me start with the core problem. Why a single configured voice breaks down in multi-entity scenarios? When you configure a voice agent with a single voice, you are making a character decision that applies for every conversation in the agent ever has. For a receptionist, that's fine. Receptionist is always a receptionist. But in museum guide scenario, the same voice speaks as Victorian era statue, then it as a Roman soldier, then a Renaissance painting. The content changes completely. The voice does not, and the mismatch is immediately noticeable. The listener's brain registered a disconnect between what the words are saying and how they sound. Voice is not just aesthetics, voice is character signal. A deep, slightly formal voice with a British accent tells the listener something about the entity before a word is spoken. A young, energetic voice signals something else. A rather gravelly voice signals something else again. If the voice does not match the character, the illusion breaks. The traditional solution is to pre-record voices for every character. You pay voice actors, record the library, and match entities to the tracks. That works for a fixed, known set of characters. It does not work when the character is dynamic, when you want to point the camera at anything and have an agent speak as it. The ElevenLabs Voice Design API solves this. You describe a voice, age, timbre, accent, energy level, period, and the API generates a new unique voice that matches that description. It is the prompt engineering layer for audio. The pipeline has 4 stages. Stage 1 is entity classification. The user points at the camera something, a statue, for example a painting or a historical artifact, and takes a photo. We send that image to OpenAI's Vision API. The Vision model, it identifies the entity and returns a structured classification, who or what this is, when they live, what their actual context was, and what personality traits we can reasonably infer. Stage 2 is the voice description generation. We take the Vision output and feed it to the language model, for example Claude, with a specific prompt, like given this entity, write a voice description for the ElevenLabs Voice Design API. The output is natural language voice description, age, accent, timbre, pacing, energy. This is the prompt engineering layer for audio. And we will spend a full slide on how we write it well. Stage 3 is voice synthesis. We call the ElevenLabs Voice Design API with the description and receive back a voice ID, a new unique voice generated to match. We cache this voice ID against the entity so we don't need to generate it again if the user returns to the same exhibit. Stage 4 is the voice switching. When the user selects an entity to talk, we load the corresponding voice ID and inject it into the ElevenLabs agent session. The agent now speaks in the generated character voice. All 4 stages are in demo repo. Let us go through each one. The vision call is the first stage of the pipeline. We send an image to ChatGPT-4 with a structured prompt that asks for entity classification in specific JSON format. The prompt asks for 4 fields: name, who or what is in the image, period, the historical era of the time period, context, a short phrase describing the cultural and social context, Roman emperor, it could be Victorian naturalist, Renaissance merchant, whatever it is, and personality traits, 3 to 5 adjectives that describe how this entity might speak. For example, confident, is it measured, philosophical, theatrical, what it is. Why ask for personality traits? Because voice description quality depends on them. Formal and measured produce a different voice than theatrical, and passionate. The vision model can infer personality from posture, expression, context, and historical record. We use those inferences as inputs to the voice description. The response comes back as a structured JSON object. We validate it against Pydantic model, entity classification, which is as the 4 fields. If the vision model returns something unexpected, Pydantic catches it before it propagates to the voice description stage. One important detail: we pass the image as base64 encoded string in the Vision API call, not as a URL. This keeps the pipeline self-contained. No external hosting required for the images. Let's go to the Visual Studio. Let's go to the Vision PY. As you can see, we read local images and bytes and convert them into the base64 data URL. Here, the request sends a structured prompt plus the image. GPT-4 returns directly into the Pydantic model. Let's run the command and see the results for this River Tiber God statue image. And let it classify. It sends the request. As you can see now, it's classified. Classical river god, ancient Roman, period. And context is represents the personification of a river or water body in classical art. Yep, it's reasonable. Let's build the voice description, the prompt engineering layer for audio. The Voice Design API generates a voice from a natural language description. The quality of that voice depends on almost entirely of the quality of the description. Here, what a bad voice description look like. An old Roman man generates something, but it is generic. It lacks character, and it gives the API very little work with. Here is what a good voice descriptions look like. A mature male voice, late 50s, with a commanding and measured tone. Deep baritone, with slight roughness, suggesting authority earned through experience. Pacing is deliberate, never rushed. Accent is formal and classical in register. The voice of someone accustomed to be listened to. The difference is specificity. You are describing a voice the same way a voice director briefs a voice actor. Age, gender, vocal register, baritone, tenor, alto, quality of the sound, warm, gravelly, smooth, breathy, pacing, deliberate, quick, measured, accent, regional, formal, collegial, similar to this. And character, finally the character, confident, tentative, authoritative, playful. In Voice Designer PY, we use Claude to generate this description from the entity classification. The prompt is: you are a voice director, given this entity's name, period, context, and personality traits, write a voice description for a text-to-speech synthesis API. Focus on age, gender, vocal register, texture, pacing, and accent. Write 3 to 5 sentences, be specific. That's it. The output of the Claude is the input of the voice agent API. Sorry, voice design API. We do not pass the entity data directly. We use Claude as an intermediary to translate structured entity data into vocal character description. If we go to Voice Designer PY, as you can see, there is built voice persona method here with description, accent, and timbre. This will be used for the Claude call. Now let us use the call Voice Design API and get back a voice. The ElevenLabs Voice Design API takes a natural language description and returns a new unique voice. The voice is not selected from catalog. It's generated fresh from your description. The API call is simple. You send a post request to the voice design endpoint with 2 fields. Text, which is your voice description, and loudness, which is controls the output amplitude. The response contains a voice ID, a string you can use in subsequent ElevenLabs API calls as if it were pre-configured voice. There is one important latency consideration. Voice generation is not fast. On a free tier account, it takes between 3 and 8 seconds to generate a voice. On a paid tier, it is closer to 1 to 3 seconds. This means you cannot generate a voice in response to a user action and have it ready immediately. You need to generate voices ahead of time, either when the user loads a session or in the background as they browse exhibits, and cache the voice IDs. In Session Manager PY, the voice cache is dictionary mapping entity names to voice IDs. When the user arrives at the new entity, we check the cache first. If we have the voice ID, we use it immediately. If not, we trigger generation and display a brief loading state while we wait. The generation runs in background asyncio task, so it does not block the rest of the session. Alright, if we go to Voice Designer PY, this First call asks ElevenLabs to design a voice from the Roman statue description. Here, the response gives us a generated voice ID and preview value. Then we persist that preview and get the reusable voice ID. If we go to Session Manager, here get or generate voice. Before generated, we check the cache. Cache it is instant, cache miss starts generation. That's it. Now let me show how to generate voices for multiple entities in parallel. In museum scenario, the user is going to encounter multiple exhibits before they start talking to any of them. This is the perfect opportunity to pre-generate voices in the background while the user is browsing. In parallel GAN PY, we use asyncio.gather to fire multiple voice design API calls concurrently. For each entity in the session's exhibit list, we create a coroutine that generates a voice description and calls the voice design API. We gather all of them and wait the result. The key insight is that generation latency compounds if you run concurrently, but not if you run in parallel. If generating one voice takes 3 seconds and you have 5 exhibits, sequential generation takes 15 seconds. Parallel generation takes 3 seconds, as long as the API handles concurrent requests, which the ElevenLabs API does on paid tiers. There is a rate limit to respect. The free tier allows 1 concurrent generation. The paid tier allows up to 5. In parallel Gen PY, we use asyncio semaphore to cap the concurrency at the appropriate limit. If you exceed it, request queue rather than fail. The result of parallel generation is fully populated voice cache before the user talks to anything. When they select the first exhibit, the voice is already there. That's the parallel Gen PY. Now let me show how to switch between these generated voices with single ElevenLabs agent session. Once we have voice IDs for multiple entities, we need to switch between them in real time as the user moves from exhibit to exhibit. The ElevenLabs Conversational Agent API supports voice ID injection at the session level. When user selects a new exhibit, we send configuration update message to active agent. WebSocket connection that changes the voice ID for subsequent utterance. The switch is seamless. The agent finishes its current sentence in the old voice and begins the next in the new one. In Session Manager PY, the active voice state is tracked as a simple dictionary, current entity and current voice ID. When the user triggers a voice switch by tapping an exhibit on a mobile screen or by saying the exhibit name, we update the state and inject the new voice into the agent connection. There is subtly worth nothing. The agent conversational context, the conversation history, the entity knowledge, the user's previous questions persist across voice switches. The voice changes, but the session does not reset. The user can ask, what were you doing when this happened? And the agent responds in the new character's voice, while drawing on the conversation history from the previous character. This persistence is important for museum-style interactions, where the user is building up a continuous narrative across multiple exhibits. The voice change signal a new character, not a new conversation. Look, this is the session manager, and it can set the voice and get the active voice, get cached voice, get or generate voice, and it can switch back and forth between the tasks, like this. Let me bring the full pipeline together with the end-of-the-end demo. The setup. We have 3 printed images, a Roman emperor, a Victorian naturalist, and a Renaissance merchant. The demo app is running on a phone. Each image card has a classify button that sends the image to the Vision API. Step 1. I classify the Roman emperor. The Vision model returns Marcus Aurelius, 2nd century AD. Roman emperor and Stoic philosopher. Personality traits, contemplative, austere, and philosophical. Claude generates a voice description, a mature male voice, late 50s, deep baritone, deliberate pacing, formal register, the measured tone of someone who has spent decades exercising self-discipline. The voice API generates the voice in about 2 seconds. Step 2. I classify the Victorian naturalist. Vision returns Charles Darwin, 19th century, British naturalist. Traits can be meticulous, curious, gentle. Voice description can be a warm male voice, mid-60s, gentle baritone with slight British cadence. Pacing is thoughtful with natural pauses. The voice of someone who chooses words carefully. Generated in the background. Step 3. I ask the Roman emperor a question. The agent speaks in the generated voice. The competitive, measured baritone, and draws on a historical context from the LLM's knowledge. I switch to Darwin, the voice changes immediately, the conversation continues. The full pipeline, image to character voice conversation, runs under 5 seconds for the first entity and is instant for cached entities. Four things to take from this episode. 1. Voice is character signal. A generated voice that does not match the entity breaks the illusion faster than any content error. Spend time on the voice description. It is the highest leverage prompt in this pipeline. 2. Specified drives quality. Bad descriptions produce generic voices. Good descriptions specify age, register, texture, pacing, and accent with concrete language, not vague adjective. Treat it like a voice director brief. 3. Generate in parallel. Cache aggressively. Voice generation has a latency. Pre-generate during the browse time. Cache every voice ID. And a cache hit is instant. A cache miss is a multi-second wait that breaks the interaction flow. 4. Voice switches. Context persist. The conversation history, entity knowledge, and user questions survive a voice switch. The voice changes, but the session does not reset. Design your agent state to reflect this. The full code in the voice agent architect lab repository. So link is in the description. In the episode 4, we go deep into the orchestration, lang graph supervisor pattern, Redis checkpointing for sub-millisecond state access, and bargain logic that lets the user interrupt the agent naturally. That is the architectural ceiling of this series. See you there. Please subscribe and like. Thank you.